in this problem, we have two coins. Coin 1 has a probability of 0.7 of coming up heads. Coin 2 has a probability of 0.6 of coming up heads. If the coin flip today comes up heads, then we select coin 1 to flip tomorrow. If it comes up tails, then we select coin 2 to flip tomorrow. If the coin initially flipped is equal likely to be coin 1 or coin 2, then what's the probability that the coin flipped on the third day is coin 1? Okay, so we have to set up the transition matrix here. Okay, so let's start with the transition matrix P. Yeah, we're going to set state 1 as coin 1 and state 2 as coin 2. So my P matrix would simply, so for 1, 2, 1, 2 here, this would be a 0.7, 0.3, because probably 0.7 coming heads, coin 1. If I get heads, then I select coin 1 again, right? So I stay with coin 1. Coin 2, 0.6 probability, because if you get heads, 0.6, you flip coin 1 tomorrow. So from 2 to 2, this will be 0.4. Okay. We need to calculate P3 after this. Okay. So once you calculate P3, 0.7, 0.6, 0.3, 0.4, you're going to end up getting 0.667, 0.666, 0.333, oops, 333, and then 0.334. Okay, you're gonna get, that's my matrix. Okay, then I want to know the probability that the coin flipped on the third day is coin 1. So then I need to know the initial probability first, right? So it tells you that it's equally likely for initial coin flip. So the alpha values are just half and half. Okay, and then I have my P3 matrix, which is PQ matrix at 0.67, 0.666, 0.333, 0.334. And I want to know the probability that the coin flipped on the third day is coin 1, right? So when I multiply these two matrices, I'm going to get a 1 by 2. And my first column, remember, this is coin 1 and this is coin 2, right? Okay, so I only need the first value. So I just have to multiply this whole thing, or so I can just multiply this whole thing out. I'm going to get two values, right? I can just read this value and that's my answer, right? Or I could take the whole thing and from the start, I just multiply this whole thing by 1, 0, right? It's like as if I'm reading that value, right? Okay. So if I do that, that will be, let's see, you can actually, we can actually just multiply these two together first as well, because this is a 2 by 2, this is a 2 by 1, okay? So then what you end up getting is 1/2, 1/2, and then if you multiply these two matrices, you end up getting just the first column, right? So 0.667, 0.666, okay? Then it's 1/2 times 0.667 plus 1/2 times 0.66. So it ends up just being 1/2, 0.667 plus, I'll just write it all out. 1/2, 0.666. Yeah. So then the whole thing becomes 0.665. So that's the probability that the coin flipped on the third day is coin 1. This problem, we have a transition matrix with 6 states. Just assume the labels are state 1, 2, 3, 4, 5, 6, all the way going down to 6. I want to know which states are transient, right? So the definition of transient state is that once you leave that state, there's a 100% probability at some point you're not going to come back to it, right? So if you can't really see this, I recommend you draw a graph if you're not sure. Okay, you can kind of tell what's going to happen here. Let's see, I think state 4 is going to be the transient one, but let's draw a graph just to make sure. Okay, so 1, 2, 3, 4, 5. I'll just draw it this way. Okay, it's probably going to be a little messy here. One's going to go to 3. I don't need even need the values. I don't really care about the values, right? As long as there's a positive value, we know there's a probability that's going to end up going there. So it's eventually going to go there at some point. From state 2, you're going to go to 6. From 3, you're going to go to 5. And then from 4, you're going to go to 1. You're also going to go to 2. And then you also go to yourself. Okay. And then from 5, you're going to go to 1. And from 6, you're going to go to 2. And then to itself. Okay, so if you take a look at this, let's take a look carefully here. I don't want to make a mistake. So let's pick my laser pointer here and see what's going on. So let's start with state 1. If I leave state 1, am I guaranteed to come back? So if I leave state 1, I can go to 3, and go to 5, and then come back to 1, right? And then go back. So yeah, it can eventually I can come back to it, right? Let's look at state 2. Yeah, let's state 2. I'm going to end up going to 6. Then I can come back to itself, right? Okay, so if I leave 2, I go to 6, and I come back to it, right? Let's get state 3. If I leave state 3, I can go to 5, and then I can come back to 1, and then come back to 3, right? So this state 3 is recurrent. State 4, you come back to itself. Once you leave state 4, though, if you leave state 4 and go to 2 or 1, either one, you won't come back to it, right? So let me draw this a little more carefully. It's a little bit confusing to see, maybe a little bit confusing. So I think this is pointing this way, right? And this is just straight, right? Okay, so the transient state here is 4, right? If you look at 5, it's going to come back, that's recurrent. 6 is occurrent. The transient state is 4, and then all the other states are recurrent. Okay, identify all closed sets of states. So there's 2 sets here, right? I'll kind of point it out in a different color here. The first one is 1, 3, and 5, right? So from 1, I can go to 3, then I can go to 5, and I come back to 1, right? Okay. States 1, 3, and 5. Once you enter one of those states, you stay in one of those 3 states. That's set forever, right? So states 1, 3, and 5 form a closed set. Okay. And the other set is going to be 2 and 6, right? So let me change up the color there so you can more easily see. So we know state 4 is transient, so we can exclude that. And then 1, 3, and 5 form a closed set. So in state 2, once you leave state 2, you're going to go to 6. Okay, you can come back to itself, but eventually it's going to come back to state 2 as well, right? Okay, so state 2 and 6 also form a closed set. Okay, is this chain ergodic? No, right? Okay, in order for it to be ergodic, it's going to be one class, or for the entire chain. This is not an irreducible chain because there's more than one class. Again, not all states communicate, so therefore this is not an ergodic chain. In this problem, we have 2 types of squirrels, gray and black, in Pine Valley. At the beginning of each year, we determine which of the following is true. Sometimes there's only gray squirrels, sometimes there's only black squirrels, sometimes there are both black and gray squirrels, and sometimes there are no squirrels at all. The transition matrix is given. We want to know what fraction of years will gray squirrels be living in Pine Valley, and what fraction of years will black squirrels be living in Pine Valley. So this is a straightforward limiting probability question, right? Oops. Okay, so I'm going to set up my states. I'm going to order the states as given. So 1 is gray, 2 is black, 3 is both, and 4 is neither. 1, 2, 3, 4. Okay, so I'm going to set it up as those 4 states. I want to know the fraction of years gross we live in Pine Valley. So let me solve the whole thing, and then we can figure out which states refer to which question. Okay, so I'm sorry. So pi1. I'm going to set up my equations. 0.7 pi1 plus 0.2 pi2 plus 0.1 pi3 plus 0.05 pi4. Right, and then we have pi2 equals 0.2 pi1 plus 0.6 pi2 plus 0.1 pi3 plus 0.05 pi4, and pi3 equals 0.05 pi1 plus 0.1 pi2 plus 0.8 pi3 plus 0.1 pi4. Pi4 is 0.05 pi1 plus 0.1 pi2. There's no here, so let's write pi4 over here so that you can kind of see how it all lines up. And then the last equation, pi1 plus pi2 plus pi3 plus pi4 equals to 1. Okay, so then I have my equations, then I can solve. So I end up getting pi1 equals 0.2857, pi2 equals 0.2381, pi3 equals 0.2857, pi4 is 0.1905. Okay, so I have all of my living probabilities. Now I just have to answer the question, right? So the question is asking for part A, during what fraction of years will gray squirrels be living in Pine Valley? So that's state 1 and state 3, right? So part A is just pi1 plus pi3, okay? And then part B, what fraction of years will black squirrels be living in Pine Valley? That's state 2 and state 3 as well, right? Okay, this is be pi2 plus pi3. So you can add up the values from up here to get the answers. Yeah, this is a pretty straightforward limiting probability question. In this problem, we have some kind of a drug processing machine. So each week, the number of acceptable quality units of a drug that are processed by a machine is observed. Greater than 100, between 50 and 100, 1 to 15, 0, indicating the machine was broken during the week. Given last week's observation, the probability distribution next week's observation is as follows. For example, if you observe a week in which more than 100 units are produced, then there's a 10% chance, 0.1 chance that during the next week, 50 and 100 units are produced. So it's probably referring to this value over here, right? Okay, so suppose last week the machine produced 200 units. On average, how many weeks will elapse before the machine breaks down? Okay, so this is a non-ergodic matrix, right? We have a set of transient and recurrent states. Okay, so if you see it right away, great. You can kind of reorder the states. You know, for me right now, I can kind of tell the absorbing state here is that 0, right? Or the last state. Once it's in 0, that means it's broken. It stays there for at least forever according to this transition matrix. So I know that's p tilde, right? So you can rearrange the matrix to get it into the form that we're familiar with, or if you see it right away, and I can tell right away, it's gonna be broken down this way, right? Okay, and then p tilde is just 1. Okay, my S matrix is gonna be 0, 0, I'm sorry, 0.05, 0.2, and 0.3. It's this vector right there, okay? And then the rest is going to be my Q matrix. 0.8, 0.1, 0.1, 0.1, 0.6, 0.1, 0.05, 0.1, 0.5. Okay, so that is my Q matrix. I want to know the number of weeks until the machine breaks down. So I need to calculate my fundamental matrix, right? So I need that Q matrix. Okay, so I'm going to take the identity minus Q and invert it, right? So that matrix is going to be 1 minus this Q matrix 0.8 minus 0.1 minus 0.05 minus 0.1. You know, I'm going to rewrite this. So it's a little bit confusing, I think. If I do 1 minus 0.8, this will be 0.2. This will be 0.4 minus 0.1 minus 0.1 minus 0.1. This will be positive 0.5. Okay. And I need to invert the whole thing. Okay. Once you invert it, you'll get the fundamental matrix. You should use some kind of software, or you can do it by hand. This is the result you get. You know what, let me write it. Let me write it over here, right in the middle. Okay, so this is my fundamental matrix. The states represented here are my transient states, right? So this is greater than 100. This is greater than 50, less than 100. And then this is 1 through 50, right? And the same thing over here on the rows, right? It's symmetric, right? So I mean, not symmetric, but it's the same order on the rows. Okay, so we want to calculate the average weeks until the machine breaks down. Suppose the last week the machine produced 200 units, so that means we're starting in. No, let me change the pointer here. I'm in this state, right? If I produce more than 200, I'm in this state currently. On average, how many weeks before it lets down? Then I just have to read across this row. This is a number of periods or transitions until absorption. So going from these transit state to one of the recurrent states, right? So I just have to add up my first row, and that's the answer to part A. Okay. Part B, suppose that last week the machine produced 50 units. On average, how many weeks before the machine breaks down? So that's referring to this third row, right? Okay. Because it's up to it's not, yeah, the third state is 1 through 50, including 50. Okay, so you add up that third row, and that's the answer to B, right? So let me explicitly write it out. Okay, so part A is going to be the first row, 6.44 plus 1.86 plus 1.02. So the whole thing is 9.32 weeks. Part B, it's the third row, 1.69 plus 1.02 plus 2.37, which is 5.08 weeks. Okay, that's the answer, and that's how you interpret this fundamental matrix M. All right, this problem, we have an insurance company, and they're charging premiums based on the customer's accident history. It gives you some values for the premiums, and it tells you a customer who has had an accident during the last year has a 10% chance of having an accident during the current year. If a customer has not had an accident during the last year, there's only a 3% chance. And the premium is based on what's happened the last 2 years, right? So um, can I set up a Markov chain to do this? I want to know the average premium paid by a customer. So I'm gonna create a Markov chain to answer this question. Yes, you can, and you have to just set up the states very carefully here. So state, the interpretation. Okay. I'll call this NN. So this means no accident last 2 years. It's kind of similar to the rain problem, right? Okay, and then it can also have, let me see if I can make it a little easier for me to write here. Okay. Also have, oops, come on. AN, so that's accident last year. No accident this year. And then I could then have NA. This is no accident last year. Accident this year. Okay, and then you have AA, accident in each of last 2 years. Okay, those are my 4 states, right? So you'll always be transitioning from one of these 4 states. Okay, so if I were to set up the transition matrix here using these 4 states, I'll kind of label it over here, and then AN and AA, so N, AN, and AA. Okay. Then from NA to NN, you have a 97% probability you still don't have an accident. Okay. Or you can get an accident, and this will be a 0.03, 0. From AN, you can also go to no accident, 0.97, 0.03. This will be 0, right? This is the case now. You go from AN to NA if you do get an accident, right? So, and then from NA, can you go to NN? You can't. You can go to AN, okay? That means that you don't have an accident, so that's 0.9. And then this can't happen. You could also go to AA, we're probably 0.1. From AA, you can't go to NN. You can also go to AN for 90% probability. And you can't go to NA, or you can go to AN, which is AA, which is 0.1. So if you get an accident, you're going to transition from AA to AA again. If you don't get an accident, you go from AA to AN. Okay, so those are my transition. That's my transition matrix. Okay, once I have this, then I can set up my limiting probabilities. Okay, because these are, let's see. I can set up my transition matrix here, because this is an ergodic matrix, right? If I start on any one of these states, I'm going to transition. I'm going to basically, all of these make up one class. They're all recurrent states, right? So I could set up my limiting probabilities here. So let's set up my limiting probabilities. Pi 1 equals to 0.97 pi 1 plus 0.97 pi 2. Pi 2 equals 0.9 pi 3 plus 0.9 pi 4. Pi 3 equals to 0.03 pi 1 plus 0.03 pi 2. Pi 4 equals to 0.1 pi 3 plus 0.1 pi 4. And then my final equation right over here, pi 1 plus pi 2 plus pi 3 plus pi 4 all my pi's, sum of all my pi's, it's gonna add up to 1. Okay. I want to know the premium, right? The average premium. So I first need to solve for these pi's, and I can find the expected value. Okay. I'm running out of space here, so let me see if I can work on the. So this is my. I've set up my Limiting Prob equations, and I can use some kind of software to get the answers. Okay. So then let me write down the pi's that I would get if I were to solve. 0.9387097. I mean, you could probably round this, but I'll just write this all out. 3, 0.029032226. By 4, 0.003225806. We want to find, you can round, right? But we want to find the average premium paid by a payoff customer by calculating the expected value, right? So, you know, we can get this. So if you go back to the question, it states that if the customer has no accidents the last 2 years, the premium is $100. If customer has an accident each of the last 2 years, then it's $400 premium. If the customer had any accident in any 1 year of the last 2 years, then the premium is $300, right? So it's pretty simple then, right? If I want to know the expected premium paid by a customer, say X is the random variable, the premium the customer pays. So again, this is a summation, xj, probably xj, right? Okay. So then this will be x1, probability of x1, plus x2, probability of x2, plus x3, probability of x3, plus x4, probability of x4. Okay. X1 is corresponding to pi 1, right? Okay, so if you go back to our states, state 1 is no accidents in the last 2 years. State 2 is 1 accident in the last 2 years. State 3 is also 1 accident in the last two years. And state 4 is accident in the last 2 years. So if you haven't had an accident in the last 2 years, the premium you pay is 100. That probably is pi 1. Okay. In state 2, you've had 1 accident in the last 2 years. So then your premium will be 300. And that's pi 2. Same thing with state 3, 300 times pi 3. And then state 4, you've had accident in the last 2 years, so you end up paying 400. Pi 4, you plug the values in, you're going to get roughly $112.58. Okay, so the expected premium that a customer pays, not knowing like what that customer actually did the last 2 years, is $112.50. That's what this result implies.